10:22 p.m. May 22nd, 2026, the Gulf of Mexico. Hurricane Arthur just dropped to 885 millibars. If this storm makes landfall the way the models are suggesting, New Orleans' levee system won't protect 400,000 people. It will trap them. But Arthur isn't even the scariest part. The scariest part is why its winds are locked at Category 2, 165 kilometers per hour, while the pressure keeps sinking, like something is coiling tighter and tighter underneath. The National Hurricane Center's supercomputers had to stop forecasting because the physics stopped making sense. Like and subscribe so you don't miss the emergency update dropping in the next 48 hours, because right now, we are the closest we've ever been to watching a city disappear. Let's go. May 18th, 2026. Somewhere in the central Gulf of Mexico, a cluster of thunderstorms quietly organized itself around a weak pressure gradient. No headlines, no emergency alerts, no breathless breaking news chyrons crawling across the bottom of television screens. The National Hurricane Center logged it as a tropical disturbance, one of dozens that spin up and dissolve every season without ever becoming anything more than a brief notation in a meteorologist's daily log. Satellite imagery showed nothing remarkable. A messy swirl of deep convection, asymmetrical, disorganized, the kind of atmospheric noise that the Gulf produces routinely from June through November, and occasionally, in recent years, as early as May. Forecasters at the National Weather Service glanced at the models, noted it as a system to watch, assigned it a low probability of development, and moved on to more pressing concerns. Nobody moved on for long. The disturbance did not dissipate. It did not drift northward and shear apart over the cooler waters of the northern Gulf Shelf, the way the climatological odds suggested it should. Instead, over the following 24 hours, it tightened. Convection. The towering columns of thunderstorm activity that act as the structural pillars of a developing tropical system began organizing around a central axis. By May 19th, a closed low-pressure circulation had formed at the surface. By May 20th, an Air Force Reserve reconnaissance flight into the system confirmed sustained winds of 65 kilometers per hour, a named tropical storm. It received its designation. Hurricane Arthur, the first Atlantic-named storm of the 2026 season, had officially entered the record books. Fast forward to May 22nd, 2026, 4 days after that unremarkable first appearance over the Gulf. The GOES 18 satellite positioned 35,700 kilometers above the equator in geostationary orbit, staring down at the Western Hemisphere with instruments precise enough to resolve individual cloud towers and track their evolution minute by minute, captured something that made forecasters in Miami stop mid-sentence. Where 4 days earlier there had been chaos, there was now geometry. A perfectly circular eye, roughly 30 kilometers in diameter, had punched clean through the cloud deck like a drill hole bored from above. The eye wall surrounding it, that dense, towering ring of the most violent convection on Earth, where the worst winds in any hurricane are concentrated, was symmetrical to a degree that atmospheric scientists rarely see outside textbook illustrations and computer-generated simulations. No ragged edges on the northwestern flank, no wobble in the circulation center, no asymmetry along the northeast quadrant that usually betrays a storm being slowly dismembered by upper-level winds. Just a perfect, almost geometric circle of organized destruction, rotating counterclockwise with mechanical precision over deep blue water, looking less like a natural weather phenomenon and more like something rendered by a graphics engine. The satellite loop played on monitors across the National Hurricane Center's operations floor in Miami. Forecasters leaned closer to their screens. Some of them had been doing this work for 20 years and had never seen a Gulf system look quite like this so early in its life. Then came the number that changed everything: 885 millibars. That figure was transmitted by a NOAAW P-3D Orion reconnaissance aircraft, one of the Hurricane Hunter planes that fly directly into storm cores as a matter of operational routine after it dropped a GPS dropsonde through the Eye of Arthur on the evening of May 22nd. 885 millibars, central pressure, the single most important number in tropical meteorology, the one that most directly encodes a hurricane's true thermodynamic intensity, independent of the complications introduced by storm size, motion, and atmospheric environment. The scale requires context, because 885 millibars is not just a low number, it is a number that belongs to a very short, very grim list. Typhoon tip, September of 1979. Still the most intense tropical cyclone ever recorded anywhere on Earth, a storm so vast that its outer circulation covered an area comparable to the continental United States. A storm that killed 99 people and sank or damaged dozens of ships reached a minimum central pressure of 870 millibars at its peak. That is the absolute floor, the lowest pressure ever measured in a tropical system in all of recorded history. Arthur, on the evening of May 22nd, sat 15 millibars above that floor. Hurricane Katrina, August of 2005. The storm that flooded 80% of New Orleans overwhelmed 53 points along the levee system and killed 1,833 people across the Gulf Coast, reached its peak intensity over the Gulf with a central pressure of 902 millibars. Arthur had already surpassed Katrina's worst moment by 17 millibars and was still deepening. Hurricane Wilma, October of 2005. The record holder for the Atlantic Basin, 982 millibars when it formed, dropping to an extraordinary 882 millibars within 24 hours in what remains the most rapid intensification event in Atlantic hurricane history, sat just 3 millibars below Arthur's current reading. Arthur was in that company. Historically, cosmically, terrifyingly rare company. And its sustained winds were 165 kilometers per hour, Category 2. That is not a misprint. 165 kilometers per hour is a serious, damaging, life-threatening hurricane. It will demolish mobile homes, strip roofs from reinforced structures, down power lines across entire parishes, and drive a wall of ocean water inland with enough force to kill anyone caught in the surge zone. But it is not by any physical logic the wind speed of a storm with 885 millibar central pressure. The two numbers cannot coexist under the rules that govern atmospheric physics. Placing them side by side is like reporting that a nuclear reactor is running at full output, but producing the electricity of a single household. The inputs and the outputs refuse to reconcile. Here is the mechanism that makes this contradiction so alarming to anyone who understands it. The gradient wind equation is the mathematical relationship that describes how wind behaves in a rotating atmospheric system. In its essential form, it states that wind speed in a tropical cyclone is a function of the pressure gradient, the rate at which pressure drops from the outer environment toward the storm's center, balanced against the Coriolis force from Earth's rotation and the centrifugal force of the circular motion itself. When the pressure at a storm's center drops to 885 millibars against an environmental pressure of roughly 1,013 millibars, the resulting pressure difference across the storm's radius is approximately 128 millibars. That gradient is immense. Under the gradient wind equation, it demands winds far exceeding Category 2. It demands Category 4 or Category 5 intensity sustained winds above 250 kilometers per hour, perhaps approaching 300? The equation is not a guideline. It is not a suggestion that nature can choose to ignore when it finds the circumstances inconvenient. It is a physical constraint as fundamental as gravity. And yet Arthur is sitting there with 165 kilometer per hour winds and 885 millibar pressure, holding both numbers simultaneously, like a locked room that cannot exist. Something external is jamming the mechanism. Something atmospheric is applying a force that physically prevents the pressure gradient from expressing itself as wind. The energy that should be driving Category 4 or 5 winds is trapped inside the system, loaded, coiled, accumulating, unable to release because the lock is still engaged. Think of it as a pressure cooker on a full burner with a jammed release valve. The temperature inside keeps climbing. The pressure keeps building. Every component of the system is under increasing stress. The cooker does not explode in that moment. It simply holds, and the question that forecasters cannot answer with certainty is not whether the valve will fail. The question is when. To understand why this is so abnormal, we first need to understand how the Gulf of Mexico actually behaves during a normal hurricane season. The Gulf of Mexico is, in geological terms, a bathtub, not a deep oceanic basin with the cold, crushing depths of the Atlantic or the Pacific, a shallow, semi-enclosed tropical basin, roughly 1.5 million square kilometers in surface area, about 1/3 the size of the contiguous United States. It is rimmed to the east by the Florida Peninsula, to the north by the arc of Gulf Coast states stretching from the Florida Panhandle through Alabama, Mississippi, Louisiana, and Texas, and to the south and west by the long curve of the Mexican coastline and the Yucatan Peninsula. The average depth across the northern continental shelf, the broad, gently sloping underwater plain that stretches offshore from the coast, is less than 100 meters in many places, shallow enough that a storm's circulation can interact with the seafloor in ways that matter. At its deepest, the Sigsbee Deep in the south-central portion of the basin descends to approximately 4,300 meters. But that geological feature is the exception. Most of the water column that directly influences hurricane dynamics sits shallow, exposed, and by late spring, warm. In May, sea surface temperatures across the northern Gulf average between 28 and 29 degrees Celsius. That range is significant in ways that go beyond simple intuition. 26 degrees Celsius is the broadly accepted minimum threshold for tropical cyclone formation and sustained maintenance, the temperature below which the ocean surface simply cannot supply enough latent heat through evaporation to sustain a storm's convective engine. Below that threshold, a hurricane starves. At 26 degrees, a storm can survive but struggles to intensify. At 28 to 29 degrees, the Gulf is supplying comfortable, reliable fuel, enough warmth to feed and maintain a Category 1 or Category 2 hurricane without dramatic effort, enough to justify the Gulf's historical reputation as a productive and dangerous hurricane breeding ground. Every season, from June through November and increasingly in May, as ocean temperatures climb earlier each year, the northern Gulf sits in this range, and storms know it. A typical hurricane in this environment follows a pattern that forecasters have studied long enough to trust. The system forms, often with surprising speed given the confined basin and the abundance of warm surface water. It reaches some level of peak intensity over the central or eastern Gulf. Then, as it tracks northward toward the coast, one of two things tends to happen. Either it encounters the cooler, shallower water of the northern shelf, which reduces the energy flux from the ocean surface and causes the storm to plateau or weaken before landfall. Or it encounters wind shear, the difference in wind speed and direction between the lower and upper levels of the troposphere, typically generated by jet stream patterns or upper-level troughs approaching from the west. Wind shear is the Gulf's most reliable natural circuit breaker. It tilts a storm's vertical structure, separates the low-level circulation from the upper-level outflow, and systematically dismantles the organized convection that keeps the thermodynamic engine running. Most serious Gulf storms get at least partially cut down by shear before they reach the coastline. The vast majority make landfall at Category 3 intensity or below. The ones that do not Camille in 1969, Katrina in 2005 become defining catastrophes. The major numerical weather prediction models have been calibrated against this baseline for decades. The Global Forecast System, the GFS, the primary American operational model, run 4 times daily by the National Centers for Environmental Prediction and the European Center for Medium-Range Weather Forecasts model, universally known in the meteorological community as the ECMWF, perform with consistent, validated skill in this environment. For a Gulf hurricane, behaving within the normal parameters of the basin, moving at a predictable translation speed, sitting over typical surface temperatures, subject to measured amounts of wind shear, the GFS delivers 48-hour pressure forecasts with a mean absolute error of roughly plus or minus 15 millibars. Wind speed forecasts carry errors of approximately plus or minus 20 kilometers per hour over the same window. These figures are not perfect. No atmospheric prediction can be, but they are operationally reliable. Emergency managers in Louisiana, Mississippi, and Texas have built their entire decision frameworks, evacuation orders, shelter-in-place guidance, resource pre-positioning, levee operation protocols on the assumption that the models will perform within those margins. When the National Hurricane Center issues a track forecast cone and an intensity forecast, the people responsible for protecting millions of lives along the Gulf Coast treat those numbers as actionable truth. That trust depends entirely on the storm behaving. Arthur is not behaving. Its position on the evening of May 22nd places it directly and precisely over the core of the loop current, and that single geographic fact invalidates every baseline assumption that the models were built upon. The loop current is not a surface temperature anomaly. It is not a warm patch, not a seasonal eddy, not a localized feature that a well-placed cold front might dissipate before it matters. It is a permanent, powerful deep-water current system, a ribbon of warm Caribbean water that enters the Gulf of Mexico through the Yucatan Channel between Mexico and Cuba, arcs northward through the Central Basin, sometimes reaching as far north as the 28th or 29th parallel, and then curves back eastward and exits through the Florida Straits to feed the northward flow of the Gulf Stream along the American East Coast. It is a structural feature of Gulf oceanography, present year-round, varying in its exact northern extent and loop geometry, but never absent, never cold, never irrelevant to any hurricane that has the misfortune or fortune, depending on your perspective, of parking above it. At the surface, the loop current runs at temperatures between 30 and 31 degrees Celsius, 2 to 3 degrees warmer than the surrounding Gulf waters in May. 2 or 3 degrees may sound marginal. It is not. The relationship between sea surface temperature and the energy available for hurricane intensification is exponential at these ranges, not linear. Every additional degree above 26 Celsius disproportionately increases the maximum potential intensity a storm can theoretically reach. 30 to 31 degrees does not produce a slightly stronger hurricane than 28 degrees. It produces a fundamentally different category of threat. But the surface temperature is not even the most important characteristic of the loop current. The critical feature, the one that separates this water mass from everything around it, and everything the forecast models assume as their default, is depth. In normal Gulf waters, the warm surface layer is thin, 30 to 50 meters, in many areas. A powerful slow-moving hurricane passing over that thin warm layer does something predictable and, from a disaster prevention standpoint, somewhat merciful. It churns the water column. The storm's circulation mixes the surface water downward and draws colder water upward from below in a process called upwelling. As cold water rises into the base of the storm, the energy available for evaporation drops sharply. The temperature contrast that drives the entire thermodynamic engine begins to erode. The storm undercuts its own fuel supply. This is why many intense Gulf hurricanes weaken faster than expected in their final hours before landfall. They have spent their ocean fuel, and the ocean has moved on over the loop current. This self-limiting process simply does not operate. The warm water, 30 to 31 degrees Celsius, extends not to 30 meters depth, not to 50 meters, but to 100 to 150 meters below the surface. When Arthur's powerful circulation churns the water column beneath it, it is not pulling cold water up from the thermocline. It is pulling up more warm water. The fuel supply is not being depleted. It is being continuously replenished from below. There is no thermal governor. There is no natural ceiling. The ocean beneath Arthur is not a shallow pool being rapidly drained. It is a deep reservoir with no visible bottom, and the storm sitting above it has been drawing on that reservoir for days. This is not a normal stretch of Gulf of Mexico. This is an oceanographic anomaly sitting directly beneath a meteorological anomaly, and the question of what the loop current is doing to Arthur below the surface is the question that changes everything about what comes next. So what is this abnormal current actually doing to Hurricane Arthur below the surface? Picture Arthur as a jet engine, not metaphorically in the loose, poetic sense structurally, mechanically, as a precise analogy for what is physically occurring inside this storm. The loop current beneath it is the fuel line continuous, pressurized, delivering high-octane thermal energy upward from 150 meters of warm water into the base of the atmosphere without pause, without depletion, without the self-limiting cooldown that kills most Gulf hurricanes before they reach their potential. The engine is running. It has been running since Arthur crossed over the loop current's northern boundary on May 20th. It has not stopped for a single hour since. But the turbine blades, the surface winds, the outward expression of all that internal power are locked. Something outside the engine is holding them back, and the fuel keeps pouring in anyway. To understand what is actually happening inside Arthur's thermodynamic cycle, you need to understand how a hurricane feeds itself under normal conditions, because Arthur is doing exactly that, just with one critical component broken. The mechanism starts at the ocean surface. Warm seawater evaporates. Water vapor rises into the base of the storm's circulation, drawn inward and upward by the low pressure at the center. As that vapor ascends through the eye wall, the dense ring of towering thunderstorms surrounding the eye, it cools with altitude. When it cools past the dew point, it condenses back into liquid droplets, cloud forms, rain falls, and in that phase, transition from vapor to liquid. Something critical happens that most people never think about. Latent heat is released, enormous quantities of it. The same energy that the ocean put into evaporating that water is now being returned to the atmosphere, directly inside the storm's core, heating the air column from within. Warmer air is less dense. Less dense air rises faster. Faster rising air evacuates the column above the storm's center more efficiently, pulling surface pressure down further. Lower surface pressure steepens the pressure gradient between the eye and the outer environment. A steeper pressure gradient accelerates the inflow of surface air toward the center. Faster inflow means more surface evaporation, more water vapor, more latent heat release. The cycle feeds itself. In atmospheric physics, this is called a positive feedback loop. Each step in the sequence amplifies the next, and under the right conditions, a hurricane does not just maintain its intensity, it accelerates it. The engine spins up of its own momentum, limited only by the ocean temperature below and the atmospheric environment above. Arthur's thermodynamic feedback loop is running at full capacity. The 885 millibar reading is the proof. That pressure did not happen by accident. It took sustained, powerful evaporation, sustained latent heat release, sustained column heating and evacuation, sustained inflow acceleration, all feeding each other in an unbroken cycle for days over the loop current's inexhaustible thermal reservoir. The engine has been producing extraordinary output. The internal pressure gradient is real, enormous, and physically demanding wind speeds far beyond Category 2. The wind speeds are not there because of wind shear. Wind shear, in the context of tropical meteorology, refers to the difference in wind velocity, both speed and direction, between different levels of the atmosphere. Specifically, the shear acting on Arthur is generated by a mid-latitude trough, an elongated region of low pressure positioned to the north over the central United States, whose upper-level flow is pushing strong westerly winds across the Gulf at altitudes between 8 and 15 kilometers. At the surface, Arthur's circulation is relatively undisturbed, but at the top of the storm at the upper troposphere, where the hurricane needs to efficiently vent its heat outward, expelling the warm air that has risen through the eye wall so that new, cooler air can descend into the eye and maintain the pressure gradient. Those westerly winds are tearing across the cloud canopy with enough force to displace the outflow layer downwind. This displacement is catastrophic for wind speed, even when it does nothing to stop the thermodynamic engine at low levels. When upper-level outflow is displaced to one side of the storm, the vertical column that connects surface inflow to upper outflow becomes tilted. A tilted column is an inefficient column. The momentum that builds through the depth of the atmosphere from surface inflow all the way to upper outflow cannot transfer cleanly into accelerating surface winds when the pathway is bent. The energy is still being generated. The heat is still being released. The pressure is still dropping at the center. But the mechanical translation of that energy into organized, symmetric, maximum surface winds is being disrupted at every level above the lower troposphere. Think of it as pressing the accelerator of a car to the floor while simultaneously applying the brakes with equal force. The engine is screaming. The tachometer is buried. Every mechanical component is under full stress. But the car is not moving at the speed the engine output would demand, because a countervailing force is absorbing all of that potential motion before it can become actual motion. The drivetrain is under tension. Something has to give eventually, either the brake or the engine. And right now, on the evening of May 22nd over the Gulf of Mexico, the brake is the only thing standing between Arthur's current reality and Arthur's physical potential. The brake is weakening. The mid-latitude trough driving the upper-level shear is forecast to shift eastward over the next 24 to 36 hours, pulling the high shear environment away from Arthur's core. As it does, the displacement of the upper outflow layer will diminish. The vertical column will straighten. The mechanical pathway between thermal energy production at the base and wind acceleration at the surface will become less obstructed, then unobstructed. And when the obstruction clears completely, when the brake releases, there is no buffer period, no gradual adjustment, no graceful transition. The energy that has been accumulating for days inside a storm, already at 885 millibars, will express itself all at once. The question is not whether the release will be violent. Physics dictates that it will be. The question is how fast and over how many hours, and whether the coastline is in the path when the maximum winds finally match the pressure that has been waiting for them. But this is not the first time nature has played this particular game, and history tells us exactly what happens when the brake lets go. August 29, 2005. Hurricane Katrina made landfall on the Louisiana coast near Burris at approximately 6:15 in the morning local time, carrying sustained winds of around 200 kilometers per hour, Category 3 intensity. It had been Category 5 2 days earlier, with peak sustained winds of 280 kilometers per hour, and a central pressure of 902 millibars over the warm Gulf waters south of Florida. By landfall, wind shear and cooler shelf waters had eroded its peak intensity. Category 3, serious but survivable. The levee system around New Orleans had been built, in theory, to handle a storm of this magnitude. 53 points along that system failed anyway. The reason was not wind, it was water. A storm surge of 8.5 meters, driven not just by Katrina's winds, but by its size, its slow forward motion, and the geometry of the Louisiana coastline funneling the Gulf inland, overwhelmed barriers that had never been designed for a surge of that scale. The Industrial Canal's floodwalls collapsed. The 17th Street Canal breached. The London Avenue Canal failed in 2 places. Water that had been pushed inland by the storm's circulation had nowhere to go and no way to stop. And it flowed into the bowl-shaped topography of metropolitan New Orleans with the patient, indifferent momentum of physics completing an equation. 80% of the city flooded. 1,833 people died. The estimated total damage exceeded $125 billion, the costliest natural disaster in American history at that time. Now hold that number alongside Arthur's 902 millibars for Katrina at peak. 885 millibars for Arthur on the evening of May 22nd. Still over open water, still constrained by wind shear, still not expressing its full intensity. Arthur is already 17 millibars deeper than Katrina ever got, and the destruction potential encoded in those 17 millibars, the storm surge, the rainfall, the inland flooding has not yet been converted into the winds and waves that will actually deliver it. The energy is loaded. The trigger has not been pulled. But there is a second storm in the historical record that matters more than Katrina for understanding what Arthur might become in the next 24 hours. And that storm is Camille. August 17th, 1969. Hurricane Camille was already a dangerous storm as it entered the Gulf of Mexico from Cuba, Category 3, organized, tracking northwestward on a trajectory that computer models of the era identified as threatening to the Mississippi coast. Emergency managers issued watches and warnings. Some evacuations occurred. People who had ridden out previous Gulf storms in their homes made the calculation, as people always do, that this one would probably be survivable too. 8 hours before landfall, Camille was still a Category 3 hurricane. 8 hours before landfall, Camille underwent a rapid intensification event that transformed it into a Category 5 storm with estimated sustained winds of 305 kilometers per hour and a central pressure of 900 millibars. In 8 hours, the National Weather Service had no satellite data capable of detecting the structural changes occurring inside the storm's eyewall. There was no GPS drops-on technology. There were no reconnaissance flights in the final hours before landfall. The forecasters, watching Camille from shore, had no way to know that the storm approaching them was no longer the storm they had been tracking. By the time the discrepancy became apparent, there was no time left to act on it. 259 people died. The storm surge along the Mississippi coast reached 8 meters in some locations, destroying everything within several hundred meters of the shoreline so completely that the debris fields were used to estimate surge height because no structures survived to mark the waterline. The parallel to Arthur is not abstract. It is operational. If the wind shear currently restraining Arthur weakens over the next 24 hours, if the mid-latitude trough tracking eastward pulls the upper-level westerlies away from Arthur's core, as forecast, the storm will not gradually and politely increase in intensity. It will undergo rapid intensification. The formal meteorological definition of rapid intensification is a sustained wind speed increase of at least 55 kilometers per hour within a 24-hour period. Camille exceeded that threshold. Hurricane Patricia in 2015 exceeded it by a factor of 3, intensifying by 175 kilometers per hour in 24 hours over the eastern Pacific. The physics that enabled both of those events, deep, warm water, low wind shear, a stable and symmetric vortex structure, are present right now over the Gulf of Mexico in a storm that is already at 885 millibars. Arthur does not need to intensify much further to become historically catastrophic. At 885 millibars, with the wind field that pressure implies, the storm surge potential alone, driven by the pressure drop's ability to physically lift ocean water, amplified by wind-driven piling, focused by the coastal geometry of Louisiana, already threatens to exceed the design tolerances of the post-Katrina levee system around New Orleans. If rapid intensification adds another 50, another 100 kilometers per hour to the sustained winds before landfall, the surge forecasts do not increment upward by a manageable margin. They enter a range that the existing protective infrastructure was explicitly not designed to handle. Camille gave the Mississippi coast 8 hours of warning. In 1969, 8 hours was already too late. In 2026, with a metropolitan area of 400,000 people, a road network that can only evacuate the region at a fixed rate, determined by highway capacity, and a population that has been told 3 times in the past 5 years that the threatening storm turned out to be manageable. 8 hours is not a contingency plan. 8 hours is a catastrophe already in progress. But Arthur is not operating alone. There is an entire system at work behind it, and that is the real reason the GFS supercomputers had to stop. 6 o'clock in the morning, Coordinated Universal Time, May 22nd, 2026, ANOAAWP3D, Orion, one of the Hurricane Hunter aircraft that fly into storm cores. Not as an act of heroism, but as a matter of scheduled operational procedure, descended through Arthur's outer rain bands and penetrated the eye wall. The crew had done this dozens of times. They knew the turbulence, the lateral acceleration, the moment when the chaos of the eye wall gives way to the eerie stillness of the eye itself. They were professionals. They had a protocol for everything. The dropsonde fell through the eye, transmitted its data. The pressure reading resolved on the display, 885 millibars. 3 seconds of silence on the cockpit voice recorder, not confusion recognition. The kind of silence that happens when a number arrives that you already knew was possible in theory and hoped you would never see confirmed in practice. The flight director read it again. Same number. He picked up the satellite phone to Miami. At the National Hurricane Center operations floor, the call arrived at 6:14. By 6:20, every senior forecaster on shift was looking at the same figure on the same screen. By 6:30, the data had been verified against the aircraft's onboard sensors, cross-referenced with the previous dropsonde pass from 4 hours earlier, and confirmed. The number was not an instrument error. It was not a calibration artifact. It was real. And it meant that Arthur had deepened overnight by another 3 millibars, while its sustained winds had moved essentially nowhere, still sitting at 165 kilometers per hour, still mechanically locked at Category 2, still holding that impossible combination of numbers like a closed fist around something it was not yet ready to release. By 9 o'clock that morning, the National Hurricane Center issued a special advisory. The language in that advisory was something forecasters there almost never use. Not expected rapid intensification. Not rapid intensification is occurring. The phrase they chose was potential rapid intensification. One word, potential, doing enormous work in the carefully calibrated vocabulary of operational meteorology, where every word in a public advisory carries legal, logistical, and psychological weight. The shift from expected to potential is not a minor stylistic choice. It is an institutional acknowledgement that the models disagree, that the physics of this particular storm are not resolving into a confident operational forecast. that the National Hurricane Center is looking at Arthur and genuinely cannot tell you with the certainty they normally provide what it is going to do in the next 24 hours. They were telling the truth in the most careful way. Bureaucratic language allows, "we do not know." While that advisory was being drafted, something was happening 500 miles to the northwest that had nothing to do with Arthur and everything to do with what Arthur was about to become. The mid-latitude trough, the elongated region of upper-level low pressure that had been positioned over the central United States for the past 4 days, driving the westerly winds across the Gulf that were maintaining the wind shear above Arthur's core, was shifting. Troughs move. This one was tracking eastward, as troughs in the westerly flow routinely do, pulled along by the planetary scale circulation of the atmosphere at altitudes where the local weather below becomes largely irrelevant to the dynamics above. The trough did not know Arthur existed. It was simply moving, following the atmospheric steering currents that govern all such systems, and as it moved eastward over Arkansas, Tennessee, the western Appalachians, it was taking the source of Arthur's restraint with it. The upper-level westerlies that had been cutting across Arthur's outflow layer were beginning to migrate away from the storm's position. The shear values above Arthur measured in knots. The unit operational meteorologists use for wind velocity at altitude had been running at approximately 14 knots on the evening of May 21st. By the morning of May 22nd, they were at 12. By noon, 11.5. The trend was not ambiguous. The brake was releasing, slowly, measurably, irreversibly, and while the atmosphere was reorganizing itself above, the ground beneath New Orleans was already failing in ways nobody was publicly discussing. The previous week had delivered heavy rainfall across southern Louisiana, not catastrophic, not headline generating, just persistent and thorough. 3 to 5 inches across the metropolitan area over 6 days. The kind of slow accumulation that fills the soil without triggering flood alerts, but leaves the ground saturated and the subsurface water table elevated. By May 22nd, the water table beneath New Orleans sat approximately 15 centimeters higher than its seasonal average. 15 centimeters. It sounds negligible. It is not. A levee system that depends on the structural integrity of earthen embankments sitting above a saturated substrate is a levee system whose safety margins have been quietly narrowed by a number that appears in no public report and generates no emergency advisory. Nobody issued an alert about the water table. Nobody inspected the embankments after the April high water event. The April event had been classified as minor. The inspection had been deferred. 3 of the 7 primary drainage pumping stations serving metropolitan New Orleans were in scheduled maintenance shutdown. Scheduled maintenance, the kind of routine operational work that proceeds according to a calendar and does not account for what is developing 600 miles to the south over the Gulf of Mexico. When those pumping stations are offline, the system's capacity to remove water from the bowl-shaped topography of the city drops to 57% of its rated maximum. 57% is manageable under ordinary circumstances. Under the storm surge projections that were beginning to emerge from the manually run HWRF model in Miami on the morning of May 22nd, 57% was not a number that appeared anywhere near the word manageable. At 2 o'clock in the afternoon, the governor of Louisiana issued a mandatory evacuation order for all coastal parishes: Jefferson, Plaquemines, Saint, Bernard, Terrebonne, La Fourche. The order was legally binding, practically difficult, and socially complicated in ways that emergency managers had spent years trying to understand and had not fully solved. 40% of the affected population did not leave. That figure is not a measure of stupidity. It is not a measure of stubbornness in the pejorative sense. It is the precise, predictable, well-documented outcome of issuing 3 mandatory evacuation orders in 5 years for storms that ultimately made landfall at intensities below their worst-case forecasts. In 2022, a storm that was projected to potentially reach Category 4 made landfall at Category 2, and the levees held. In 2023, an evacuation order went out for a system that weakened to a tropical storm before it reached shore. In 2024, a storm tracked 50 miles east of the projected cone, and the western parishes saw little more than heavy rain. Each of those events was, from the perspective of the atmospheric science, a legitimate near miss. Each of those events was, from the perspective of a family that had spent $300 on a hotel room in Baton Rouge and returned home to find their house undamaged, evidence that the warnings were excessive. The science and the lived experience produced completely opposite conclusions about the same events, and the lived experience had won. 160,000 people were in the projected impact zone on the afternoon of May 22nd, and they were not leaving, because history had taught them incorrectly, dangerously, through no fault of their own, that the forecast was probably wrong. To understand why all of this is converging in one place, we need to go deeper than the surface, down to what the loop current is actually doing to Arthur from below. The loop current is not a feature of the Gulf of Mexico in the way that a reef or a sandbar is a feature. It is not static. It does not sit still and wait to be encountered. It is a river inside an ocean, a continuous, powerful, warm water current that flows northward out of the Caribbean Sea through the Yucatan Channel. The passage between the Yucatan Peninsula and the western tip of Cuba, at depths and velocities that make it one of the most energetically significant oceanographic structures in the Western Hemisphere, it enters the Gulf. It curves. In some years, the loop extends as far north as the 28th or 29th parallel before bending back eastward. In other years, it stays compressed in the south-central basin, shedding warm core eddies, rotating pools of warm water that detach from the main current and drift westward, slowly cooling over months as they lose contact with their source. The eddies matter enormously to Gulf hurricane dynamics. The main current matters more. And on May 22, 2026, Arthur is not sitting on an eddy. It is sitting on the main current itself, directly above the core of the loop, at the point where the warm water is deepest, most continuous, and most thermodynamically potent. Surface temperature 30 to 31 degrees Celsius. That number alone, 2 to 3 degrees above the surrounding Gulf, is enough to explain why Arthur has deepened as far as it has. But surface temperature is the least important characteristic of what is beneath this storm. Think about what a normal hurricane does to the ocean beneath it. The circulation is powerful wind-driven mixing at the surface, combined with the pressure drop-induced upwelling at the center, churns the water column. Warm surface water gets pushed outward and downward. Colder water from below the thermocline from 30, 40, 50 meters depth gets pulled upward into the base of the storm. That cold water makes contact with the overlying atmosphere. The temperature differential that drives evaporation drops. The latent heat flux from ocean to atmosphere weakens. The storm's energy supply is being cut off by the storm's own mechanical action, a self-limiting process that meteorologists consider one of the ocean's more reliable circuit breakers. Many Gulf hurricanes weaken in their final 12 to 24 hours before landfall for exactly this reason. They have consumed the warm water beneath them and brought up the cold. Over the loop current, that process does not happen. The warm water, 30 to 31 degrees, does not occupy a thin surface layer. It extends downward through 100 to 150 meters of the water column. When Arthur churns beneath itself, it is not pulling cold water up from the thermocline. There is no thermocline within reach. The upwelling delivers more warm water from deeper in the same thermal reservoir. The storm cannot undercut its own fuel supply because the fuel goes deeper than the storm can dig. The thermal governor that limits every other Gulf hurricane does not exist here. The number that quantifies this is ocean heat content, not sea surface temperature that tells you what is happening at the interface between ocean and atmosphere. Ocean heat content tells you how much total thermal energy is stored through the depth of the warm layer, expressed in kilojoules per square centimeter. It is the metric that actually predicts rapid intensification potential. Because a storm does not just interact with the surface, it interacts with the entire warm water column as it mixes and churns during its passage. In the region where Arthur is currently located, ocean heat content readings from NOAA's operational analysis run at 120 to 140 kilojoules per square centimeter. The significance of that range requires a specific reference point. After Hurricane Katrina, a series of post-event studies examining why Katrina intensified as explosively as it did over the loop current in 2005, and why the models failed to capture the full intensity identified 100 kilojoules per square centimeter as the threshold value above which rapid intensification becomes operationally credible. Not guaranteed, not automatic. But credible, the oceanographic conditions are sufficient to support it. Arthur is sitting at 120 to 140, 20 to 40 kilojoules above the threshold. In a system where the difference between Category 3 and Category 5 is a matter of sustained thermodynamic support over 12 to 18 hours, that margin is not academic. Rapid intensification has a formal definition. It is not simply getting stronger fast. The World Meteorological Organization and the National Hurricane Center define it as a sustained wind speed increase of at least 55 kilometers per hour within a 24-hour period. 55 kilometers per hour. In practical terms, that is the difference between a Category 2 and a Category 4 storm in a single day. Historically, rapid intensification events in the Gulf have occurred under three simultaneous conditions: ocean heat content above 100 kilojoules per square centimeter, wind shear below 10 knots, and a structurally stable and symmetric vortex with a well-defined eye. Those three conditions function as a set. All three present the probability of rapid intensification rises sharply. 2 of 3 uncertain, 1 of 3 unlikely. Arthur currently satisfies 2 of the 3. Ocean heat content 120 to 140 kilojoules per square centimeter. Vortex structure a 30-kilometer eye of near-perfect symmetry, captured repeatedly by GOES-18 and confirmed by reconnaissance. Those 2 boxes are checked, definitively, unambiguously. The third condition, wind shear below 10 knots, is the only thing standing between Arthur's current state and the physical conditions that produce historically catastrophic storms. And at 12 noon on May 22nd, the shear above Arthur measured 11.5 knots. At the rate it has been declining over the past 18 hours, the 10-knot threshold will be crossed sometime between 3 and 6 in the morning. Coordinated Universal Time on May 23rd, which brings us to the global forecast system and why it stopped. The GFS is not a simple extrapolation engine. It is one of the most computationally complex numerical weather prediction systems on Earth, a model that divides the atmosphere into a 3-dimensional grid of millions of cells, applies the fundamental equations of fluid dynamics and thermodynamics to each cell at each time step, and advances the entire system forward in time to produce a forecast. It runs 4 times daily. It has been validated against decades of observed weather data. Under normal conditions, for a Gulf hurricane behaving within the established parameters of the basin, it performs well. Arthur is not within the established parameters. The coexistence of 885 millibar central pressure with 165 km/h sustained winds represents a physical state that falls outside the solution space the model's equations are designed to navigate. When the GFS initialization algorithms attempt to set up the storm's initial state, assigning wind speeds, pressure gradients, and thermodynamic variables to each grid cell in a way that is internally consistent with the governing equations, the 885 millibar pressure demands wind speeds that contradict the observed 165 kilometers per hour. The model has no stable way to reconcile the two values. It generates what numerical modelers call divergent solutions forecast runs that produce wildly different outcomes depending on tiny variations in the initial conditions. The model equivalent of a pencil balanced on its tip, one infinitesimal perturbation in one direction sends the answer completely differently than an infinitesimal perturbation the other way. When a model produces divergent solutions across its ensemble runs, the spread of the forecast is not a range of equally probable outcomes. It is a sign that the model's mathematical framework has reached a region of state space where it cannot reliably operate. The decision to halt the GFS runs and shift to manual intervention was made by senior forecasters at the National Centers for Environmental Prediction in College Park, Maryland. It was the correct decision. It was also an event with no recent precedent in the operational history of American hurricane forecasting and admission in institutional form that Arthur had moved into territory where the standard computational tools were producing more noise than signal, and that human judgment applied to the HWRF model run manually was more reliable than automated model output from a system not built for this specific physical configuration. And when all of these conditions finally begin to lock into alignment with each other, there is a physical threshold that, once crossed, cannot be undone. The research that matters most here is not recent. It was published in 2003 in the Journal of Climate by two scientists named Kaplan and DeMaria, working with the Statistical Hurricane Intensity Prediction Scheme dataset. Their analysis examined every Atlantic rapid intensification event in the historical record and asked a simple question: what combination of environmental conditions, when present simultaneously, produces the highest probability of rapid intensification within a 24-hour window? The answer was not complicated. When wind shear drops below 10 knots and ocean heat content exceeds 100 kilojoules per square centimeter at the same time, the probability of rapid intensification occurring within the next 24 hours rises to 67%, 2 out of 3. That study remains the standard reference document at the National Hurricane Center for rapid intensification probability assessments. It has been tested against 20 additional years of storms since publication. It holds 67% is not certainty, but it is the kind of number that, when it appears in an operational forecast discussion at 2 in the morning, makes people stop using the word if and start using the word when. At 6 in the evening, Coordinated Universal Time. May 22nd, 12 hours after the Hurricane Hunter confirmed 885 millibars, 9 hours after the potential rapid intensification. Advisory went out. The measured wind shear above Arthur's core stood at 14 knots. Ocean heat. Content in the storm's immediate vicinity, 128 kilojoules per square centimeter, 28 above the threshold. The storm's forward translation, speed 9 kilometers per hour. That last number deserves a moment because it is doing something specific and dangerous that the pressure and wind figures alone do not capture. A hurricane moving at 9 kilometers per hour is nearly stationary. At that translation speed, any given point on the ocean surface directly beneath the storm remains under the circulation's influence for an extended period, not the 8 to 12 hours that a fast-moving storm might subject it to, but potentially a day or more of continuous mechanical stirring, evaporation, and heat extraction. For a normal hurricane over a shallow warm layer, slow translation speed is actually self-limiting. The storm stirs out its own fuel faster, brings up cold water faster, and weakens. Over the loop current, where the warm water is 100 to 150 meters deep and cannot be exhausted by stirring. Slow translation speed is the opposite. It maximizes the contact time between the atmosphere and the thermal reservoir. 9 kilometers per hour means Arthur has been drawing on the same stretch of loop current water for more than 30 hours. 30 hours of uninterrupted heat extraction from a reservoir that has not cooled by a measurable amount. The system is not being depleted. It is being used continuously to its maximum thermodynamic potential by a storm that is moving just fast enough to technically qualify as moving. The 14-knot shear reading at 1800 Coordinated Universal Time on May 22nd represents a 4-knot drop over the previous 24 hours. 4 knots in 24 hours. If that rate of decline continues and the synoptic pattern driving it, the eastward progression of the mid-latitude trough gives no indication of reversing the 10-knot threshold, will be crossed somewhere between 3 and 6 in the morning, Coordinated Universal Time, on May 23rd. That window is 9 to 12 hours from the evening of the 22nd. In Atlantic hurricane terms, 9 to 12 hours is the difference between a forecast and a fait accompli. Here is what synchronization actually looks like when it happens. The moment wind shear drops below 10 knots, the displacement of Arthur's upper outflow layer the mechanical tilting of the vertical column that has been preventing the pressure gradient from expressing itself as wind begins to correct. The outflow straightens. The pathway from surface inflow at the base of the eye wall to upper level outflow at the top of the troposphere becomes vertical, efficient, unobstructed. The latent heat released by condensation inside the eye wall, which has been heating the column for days, now has a direct mechanical route to the surface winds. The energy is not newly generated. It has been accumulating. It does not need to be produced in that moment. It needs to be released. And release in a system already at 885 millibars with a symmetric 30-kilometer eye sitting above 128 kilojoules per square centimeter of ocean heat content is not a gradual process. A symmetric, stable vortex at 885 millibars with no wind shear and unlimited thermal fuel has one equilibrium state available to it, maximum potential intensity. The equations do not offer alternatives. Once the constraint is removed, the storm moves toward that equilibrium, and it moves fast. Because the energy required to accelerate from Category 2 to Category 4 or 5 winds is already stored in the pressure gradient that wind shear has been suppressing. The storm does not need to generate that energy. It needs to convert it. Conversion, once the mechanical obstruction is gone, happens over hours, not days. The hurricane weather research and forecasting model, run manually by the team in Miami after the global forecast system produced divergent solutions, returned its output in the early afternoon of May 22nd. The forecast range it produced was not narrow. Manual model runs, by their nature, acknowledge uncertainty explicitly in a way that automated ensemble averages can obscure. The HWRF gave a spread Category 3 to Category 5, with sustained winds potentially exceeding 250 kilometers per hour, achievable within 18 to 30 hours of the shear threshold being crossed. 18 to 30 hours. If the threshold breaks at 3 in the morning on May 23rd, and the lower bound of that window holds, Arthur could be at Category 5 intensity before midnight on the same day. If the upper bound holds, the intensification plays out more slowly and the storm makes landfall at a lower peak. The range between those two outcomes is the range between a bad hurricane and a historical catastrophe, and the HWRF model, running on everything available, cannot collapse that range further. The atmosphere has not decided yet. The physics will decide between 3 and 6 in the morning, and the physics will not be consulting anyone's preference about the answer. But even if Arthur does not reach Category 5, even if the shear holds longer than projected, even if a dry air intrusion from the Mexican interior finds its way into the storm's core and disrupts the convective structure, even if the intensification stalls at Category 3 and the worst-case model runs turn out to be wrong, the defensive layer that millions of people are counting on to protect them is already not what it appears to be. After Katrina, the United States Army Corps of Engineers spent 8 years and $14.5 billion rebuilding the hurricane protection system around metropolitan New Orleans. The project, called the Hurricane and Storm Damage Risk Reduction System, was the largest civil engineering undertaking in American history at the time of its completion. New flood walls, reinforced earthen levees, massive surge barriers at the mouths of the major waterways, the Lake Bourgogne-Surge barrier, the largest in-the-water barrier ever constructed in the United States, stretching 1.8 miles across the Bienvenue Gap, pump stations rebuilt to handle volumes of water that the pre-Katrina system could not approach. The design standard for the entire system protection against a storm producing a 4.5-meter surge, roughly the surge associated with a major Category 3 hurricane approaching from the most dangerous quadrant. $14.5 billion. Completed in 2013. Tested against Isaac in 2012 and performing within specifications. It sounds like the problem was solved. The problem was not solved. It was deferred. New Orleans sits in a bowl. That is not a metaphor. It is literal topography. Large portions of the city's residential areas lie below mean sea level, some as much as 2 meters below. Because the city was built on deltaic sediments that have been compressing and settling under their own weight for as long as humans have lived there, the entire metropolitan area is sinking. The technical term is subsidence, and in New Orleans, it is relentless, 8 to 12 millimeters per year in most areas, faster in some, slower in others, driven by the compaction of organic-rich alluvial sediments, the extraction of groundwater and petroleum from the subsurface, and the elimination of sediment replenishment that the Mississippi River once provided naturally before the levees channeled its flow directly to the Gulf. 8 to 12 millimeters per year does not sound dramatic. Run it forward 20 years from the completion of the rebuilt system in 2013 to May 2026, and certain levee segments have settled between 160 and 240 millimeters below their design elevation. 15 to 20 centimeters of effective height loss. The concrete flood walls, which cannot settle the way earthen embankments can, have in some locations pulled slightly away from the earthen sections they connect to, creating contact points that are geometrically correct on paper, but mechanically imperfect in practice. None of this has triggered a formal remediation project. Budget cycles at the Orleans Levee District do not accommodate continuous structural adjustment for continuous geological processes. The inspections occur. The reports note the settlement figures. The funding is not allocated. The levees stand at their current elevation. And their current elevation is not the design elevation anymore. Against a 4.5-meter surge, the system was built to hold. Against 5.5 to 7 meters, the range that Arthur's combination of 885 millibar central pressure, 9 km/h forward speed, and the funnel geometry of the Louisiana coastline is producing in the HWRF surge model, the engineering math does not work. The geometry of hydrostatic pressure against an earthen embankment at that water height exceeds the resistance the structure was designed to provide. This is not speculation and it is not pessimism. It is the Corps of Engineers' own design specifications applied to a set of conditions that the design specifications did not contemplate, because no one building the system in 2013 designed it for the storm that is currently sitting 885 millibars deep over the loop current. 160,000 people are still in the projected impact zone as of the evening of May 22nd. The mandatory evacuation order for coastal parishes was issued at 2 in the afternoon. The contraflow plan reversing inbound highway lanes to outbound to increase evacuation capacity was activated within the hour. The road network can move a certain number of vehicles per hour. That rate is fixed by physics and infrastructure, not by the urgency of the situation. Running the evacuation numbers against the remaining population suggests that the road network, operating at maximum contraflow capacity, can clear the remaining residents in approximately 36 to 48 hours of uninterrupted traffic flow. 36 to 48 hours. The HWRF's fastest intensification scenario puts Category 4 or 5 conditions over the coast in 18 to 30 hours. The math does not clear. The people who remain are not evenly distributed across demographics. The elderly, disproportionately. People without vehicles, and in a city where car ownership correlates with income, and where poverty rates in the lowest-lying neighborhoods are among the highest in the state. No vehicle is not an edge case. People with medical dependencies, oxygen equipment, dialysis schedules, mobility limitations for whom evacuation is not a matter of packing a bag and getting on the highway. And, cutting across all of those categories, people who have done their own actuarial calculation based on their own experience and concluded that the storm will probably not be as bad as the forecast says. 3 of the 7 primary drainage pumping stations serving the metropolitan area remain in scheduled maintenance shutdown. They have been in that state for 11 days. The maintenance cycle was scheduled to end on May 28th. If the levee system is overtopped or breached before, then if water enters the bowl faster than the 4 operational stations can remove it, the city's ability to drain itself is capped at 57% of rated capacity. 57% of rated capacity was designed for rainfall events and minor flooding. It was not designed for the scenario where the surge barrier at Lake Bourne is overtopped and water begins moving across the landscape in volumes measured not in centimeters, but in meters. The $14.5 billion system, the best engineered hurricane protection structure in American history, was built for a storm it is not facing. The land beneath it has settled in ways that reduced its effective height without triggering a repair budget. The people it was built to protect are 40% still inside its boundaries, and the pumps that would remove the water if the barriers fail are 43% offline. This is the defensive layer. This is what stands between Arthur's current trajectory and the question that everyone in that operations room in Miami is not quite saying out loud yet. This is the moment we need to stop, breathe, and look honestly at what the science actually knows, and more importantly, what it does not. Let's stop for a moment. Before we go any further, before we talk about what might happen, what could happen, what the models are screaming at us, we need to clear the air. Because every time a storm like this appears, the internet does what the internet does. The conspiracy theories start within hours. By now, your feed is probably already full of them. So, let's get this out of the way. No, HAARP did not create Arthur. The High Frequency Active Auroral Research Program is a research facility in Alaska that studies the ionosphere, the uppermost layer of the atmosphere, roughly 100 to 1,000 kilometers above the surface. It does not control weather. It cannot steer hurricanes. The physics do not work that way, and anyone claiming otherwise is either deeply confused about atmospheric dynamics or deliberately misleading you for clicks. Arthur formed because the Gulf of Mexico in May of 2026 is unusually warm, because a low-pressure disturbance drifted over the loop current at exactly the wrong moment, and because the atmospheric conditions aligned in a way that happens to be catastrophically rare. That's it. No hidden hand, no government program. And no, The National Hurricane Center is not hiding the real forecast. The GFS suspension is not a cover-up. When a numerical weather model produces what meteorologists call divergent solutions, meaning it runs the same scenario multiple times and gets wildly different answers each time, the standard protocol is to pause, flag the run, and hand it to human forecasters for manual review. That's not suppression. That's quality control. It's the scientific equivalent of a surgeon stopping mid-procedure because the imaging equipment starts giving contradictory readings. You don't push through. You stop, reassess, and make sure you're not about to make a catastrophic error. The GFS team did exactly what they're supposed to do. What I want you to understand is this: the uncertainty around Arthur is not manufactured. It is real, and it runs much deeper than most coverage is willing to admit. Here's the honest state of the science right now. After 50 years of dedicated research satellites, reconnaissance aircraft, ocean buoys, supercomputer modeling, we still cannot forecast rapid intensification with accuracy above 70%. 70%. That means roughly 3 in 10 RSAS-I events catch us off guard. Or we predict intensification that never happens. For something with the potential consequences of a Gulf Coast landfall, that margin is enormous. And we've known about this gap for decades. We fund research into it. We publish papers about it. We have not solved it. The interaction between eyewall structure and wind shear is still, in the language of atmospheric scientists, a partially open question. We know wind shear disrupts a storm. We know it tilts the vortex, ventilates the warm core, and suppresses convection. But the precise way a storm's inner architecture responds to shear the asymmetries, the pulses, the moments when a storm fights back against its environment, that is still a black box to a meaningful degree. The equations describe the broad strokes. The details are where storms surprise us. Ocean heat content is a necessary condition for rapid intensification. It is not a sufficient one. Arthur sits over 128 kilojoules per square centimeter of thermal energy, far above the threshold identified in post-Katrina research. That tells us the fuel is there. It does not guarantee the engine will ignite. Other factors have to cooperate. And this is where the story gets complicated in ways that the standard forecast discussion rarely touches. There are variables in this system right now that are receiving almost no media attention. I want to name them directly because they matter. The first is stratospheric temperature above the storm. Satellite data from the 22nd of May shows the lower stratosphere, the atmospheric layer sitting above Arthur's convective towers, is running unusually cold for this time of year. That matters because cold air aloft increases the temperature gradient between the storm's warm core and the surrounding atmosphere, which strengthens the convective engine independently of what's happening at sea level. In other words, even if wind shear does not decrease, anomalously cold air in the stratosphere can push convection harder on its own. This is a mechanism that drives rapid intensification, sometimes without the classic wind shear trigger. It is not widely discussed in public briefings. It is real. The second quiet variable is the eye wall itself. If Arthur undergoes what's called an eye wall replacement cycle, a process where a new outer eye wall forms, contracts, and eventually chokes off the original inner eye wall, the storm will appear to weaken temporarily on satellite imagery. Wind speeds drop, pressure stabilizes, or even rises slightly. People watching the data might exhale. But when the outer eye wall fully takes over and consolidates, the storm often reemerges stronger than before, with a larger wind field that pushes storm surge across a wider area. An ERC mid-intensification phase, right before landfall, is one of the hardest scenarios to communicate to the public because the apparent weakening creates false reassurance at exactly the wrong moment. The third variable is forward speed. Arthur is currently moving at approximately 9 kilometers per hour almost stationary. If it accelerates northward toward the Louisiana coast at more than 20 kilometers per hour, the storm surge equation changes dramatically. Faster movement means less time for the surge to pile up against the coastline, which reduces maximum water height. But it concentrates the most destructive winds into a tighter time frame, which can actually increase structural damage to buildings and infrastructure. A faster-moving Arthur might not flood New Orleans to the same catastrophic depth, but it could shred coastal communities with sustained extreme winds in a way that a slow-moving storm doesn't. It's a different flavor of disaster, not a lesser one. None of these variables are fringe speculation. They're in the scientific literature. They're in the operational forecaster's mental checklist. They just don't make it into the 60-second television segment because they're genuinely hard to explain quickly, and they don't resolve into a clean single number you can put on a graphic. With all of those variables on the table, there are two scenarios sitting at opposite ends of what's possible, and both of them have legitimate scientific grounding. The HWRF ensemble, running manually after the GFS suspension, puts the probability of this scenario at somewhere between 40 and 45%. That makes it the single most likely individual outcome, and I want to walk through it carefully because most likely does not mean harmless. Here's how it unfolds. Wind shear does not decrease fast enough. The trough of low pressure sitting off the Texas coast, which has been weakening over the past 18 hours, stalls before it fully collapses. Maybe a ridge of high pressure to the northeast holds it in place longer than the models anticipated. The shear stays above 12 to 14 knots, not catastrophically high, but enough to keep disrupting Arthur's upper-level outflow and prevent the storm from fully organizing its convective structure. Or, and this is the alternative mechanism, a dry air intrusion sweeps in from Mexico. The Gulf of Mexico sits adjacent to some of the driest air masses on the continent, and when that air gets pulled into a storm's circulation, it acts like sand in a gear. Dry air suppresses convection. It erodes the eye wall from the inside out. It can stall intensification for 12, 18, 24 hours, long enough for the storm to cross into shallower water and lose its thermal foundation before ever breaking through the conditions needed for rapid intensification. In this scenario, Arthur makes landfall as a Category 2 to Category 3 hurricane. Wind speeds at the coast run between 180 and 200 kilometers per hour. Storm surge reaches 3 to 4 meters at the most exposed points, still catastrophically dangerous for anyone caught in low-lying coastal areas. But below the design threshold of the post-Katrina levee system, New Orleans does not flood. The inner city levees hold. Now, stop right here, because I need to push back against any instinct to read that paragraph as good news. A Category 3 hurricane making landfall on the Louisiana coast is still a major disaster. Infrastructure takes severe damage. Power outages affect hundreds of thousands of people for days or weeks. Coastal communities outside the levee protection zone face life-threatening flood conditions. Storm surge of 3 to 4 meters inundates neighborhoods that have never been inside any protected zone. People die realistically. Dozens of people, concentrated in the areas that received inadequate warning, that couldn't evacuate in time, or that chose not to leave. The physical destruction is real. The human cost is real. This is not a non-event, but, and this is the part that haunts emergency managers more than the storm itself, there's a second-order consequence that could ultimately be more dangerous than anything Arthur does in this scenario. This would be the 4th mandatory evacuation order in the greater New Orleans area within 5 years. The 4th time residents packed their cars, drove hundreds of kilometers to relatives' houses or evacuation shelters, disrupted their jobs, spent money they may not have had, and came home to a city that was mostly intact. The 4th time the order felt, in retrospect, like an overreaction. The research on this is clear, and it's grim. Each successive false alarm reduces compliance with the next evacuation order by a measurable percentage. The exact figures vary by study, but the direction is consistent, and it is not good. People who have evacuated multiple times for storms that did not materialize begin to perform their own risk calculation. They weigh the cost and disruption of leaving against their memory of returning to find their home undamaged. They begin to doubt the forecasters. They make the rational-seeming decision to shelter in place. And then one day, the storm is real. That is the trap embedded inside the best-case scenario. If Arthur stays at Category 2 or 3, if New Orleans avoids catastrophic flooding, the immediate crisis passes, but the institutional credibility of emergency warnings erodes by another increment. The next storm that threatens this city will face a population slightly more resistant to evacuation orders, slightly more certain that the warnings are always exaggerated, slightly less likely to leave when leaving might save their lives. The false alarm is survivable, but it plants a seed that, under the right conditions, becomes its own kind of catastrophe. But if the envelope flips the other way, if wind shear releases at precisely the moment Arthur is still sitting over the loop current, then Scenario 2 stops being a hypothesis, 25 to 30%. Before you dismiss that, before your brain files it under unlikely and moves on, sit with what that number actually means. 1 in 4. If you sat down at a table and someone told you there was a 1 in 4 chance the chair would collapse under you, you wouldn't sit. You'd find another chair. 25 to 30% is not a tail risk. It's not a rounding error. It's a coin flip with 2 heads and 2 tails. And right now, one of those tails has the word catastrophic written on it. Here's how it unfolds if it unfolds. The critical window is between 3 and 6 in the morning, UTC, on May 23rd. That's late night on the 22nd for the Gulf Coast. Most people are asleep. The news cycle has quieted. And somewhere in the upper atmosphere above the Gulf of Mexico, the trough of low pressure that has been holding Arthur's wind shear in place finally collapses. The shear drops below 10 knots. That's hour 0. What happens in the 6 hours after hour 0 is not gradual. Rapid intensification is not a slow climb. When the conditions align, when OHC is at 128 kilojoules per square centimeter, when the upper atmosphere clears, when a well-organized eye wall suddenly gets handed unlimited fuel and no resistance, the storm doesn't ease into it. It lunges. Wind speeds jump from 165 kilometers per hour to over 230 kilometers per hour. Not over days. In 6 hours, the central pressure, already sitting at 885 millibars, keeps drilling downward. The eye, which has been roughly 40 kilometers across, contracts as the system tightens. 15 to 20 kilometers, smaller, denser, more violent per unit of space than almost anything the atmosphere produces. At that size, the eye of Arthur would fit inside Manhattan with room to spare on both sides. And the eye wall wrapped around it, the annular ring of the most extreme winds on Earth, would be sitting directly over the urban core of whatever coastline it strikes. 6 hours of sleep. That's all the gap between a Category 2 and what comes next. The 18 to 24 hours after that are where the geography of Louisiana stops being an inconvenience and starts being a death trap. As Arthur pushes northward into shallower coastal water, something counterintuitive happens. The storm surge grows. Deep water dissipates wave energy. Shallow water compresses it. The continental shelf off Louisiana is among the flattest, shallowest stretches of seafloor on the Gulf Coast, a geometry that acts like a ramp, concentrating and amplifying whatever the storm pushes ahead of it. By the time Arthur's surge reaches the mouth of the Mississippi River and the southern edges of Lake Pontchartrain, the water column has been compressed, accelerated, and stacked to a height of 5.5 to 7 meters above normal sea level. 7 meters. That's roughly the height of a 2-story building, moving horizontally, carrying debris, sediment, and enough kinetic force to peel the facing off reinforced concrete structures. Now, the levees. The post-Katrina system was designed and built after 2005 at a cost of $14.5 billion. Engineers designed it to withstand a Category 3 storm with a surge of 4.5 meters. It is, by any honest accounting, a remarkable engineering achievement. It is also 20 years old, sitting on land that has been sinking at 8 to 12 millimeters per year, and it has never been tested against what Arthur is about to deliver. The first failure point is the eye wall along the Industrial Canal, the same section that breached during Katrina in the same neighborhood, for many of the same structural reasons. The geometry of the eye wall concentrates hydrostatic pressure along its base. When surge height exceeds the design envelope, the soil beneath the wall begins to saturate and lose its bearing capacity. The wall doesn't shatter, it tilts, it slides, and then it's gone. Within 45 minutes of that first breach, water is moving through the lower Ninth Ward, not trickling, moving. The way water moves when a pressure differential is suddenly resolved fast, purposeful, filling every low point simultaneously. Streets become channels, ground floors become sumps. Anyone who did not reach the second floor or higher before that moment is now in a survival situation. And then the cascade begins. The breach at the Industrial Canal changes the hydrostatic pressure distribution along every adjacent levee section. Water that was being held back now has a path, and that path makes the remaining walls work harder to contain what's left. The weakest points, the sections where 20 years of subsidence have shaved 15 to 20 centimeters off effective height, begin to fail in sequence, not all at once, one after another, each failure increasing the pressure on the next. 3 of the 7 major pump stations in New Orleans are offline for scheduled maintenance. This was routine. Nobody planned a hurricane around it. Under normal circumstances, taking stations offline in rotation is standard infrastructure management. Under these circumstances, it means that when water starts entering the city, the system designed to push it back out is operating at 57% capacity. The water has nowhere to go. 160,000 people chose not to evacuate. Some couldn't. Elderly residents, people without vehicles, people who weighed the cost of leaving against the memory of 3 previous false alarms and decided to stay. Some didn't believe it would be this bad. Some thought the levees would hold. They're all still in the city now, and the city is filling. The long-term accounting hasn't been written, yet it can't be. This scenario hasn't happened. But the estimates exist. Damage exceeding $200 billion US. That's the direct figure: destroyed housing, wrecked infrastructure, contaminated soil, flooded industrial facilities. It doesn't capture what happens to a city's tax base when 100,000 residents don't come back. It doesn't capture the federal cost of prolonged emergency response. And it doesn't capture the question that will follow, the one that was asked quietly after Katrina and will be asked loudly after this. Should New Orleans be rebuilt again after Katrina? That question was treated as almost unspeakable, morally offensive, geographically defeatist. 20 years later, with sea levels measurably higher, with the land measurably lower, with the climate system measurably warmer, the question will not be so easy to dismiss. 400,000 people live in a city that sits below sea level, protected by barriers that were designed for a different storm in a different ocean. If those barriers fail in 2026, the debate about the city's future will not be theoretical anymore. That's scenario 2, 1 in 4. So what do we do with these 2 scenarios? Not sit and wait for fate, but know exactly which signals to watch for in the hours ahead. I'm not going to tell you Arthur will reach Category 5. Nobody knows that. Not the National Hurricane Center, not the HWRF ensemble running manually in Miami right now. not the reconnaissance crew who flew into the eye this morning. The atmosphere doesn't telegraph its intentions cleanly, and anyone claiming certainty in either direction, either this will be apocalyptic or this will fizzle out, is selling you something. What I can give you is better than a prediction. I can give you 5 specific signals. Watch these, and you'll know which scenario is unfolding before the official advisory tells you. The first signal is wind shear, and you can track it yourself. Sites like Tropical Tidbits and Weather Underground carry near real-time shear analysis that updates every few hours. What you're watching for if wind shear drops below 10 knots in the next 12 hours. The primary break on Arthur's intensification is gone. That single data point shear crossing below 10 knots is the clearest early indicator that rapid intensification is no longer just possible, but probable. Above 15 knots, the storm is still constrained. Between 10 and 15, it's contested. Below 10, the door is open. The second signal is central pressure. Arthur is currently at 885 millibars, already in territory that shocks most meteorologists given the storm's current wind speeds. If you see that number drop below 880 millibars, pay attention. If it drops below 875, Arthur is entering historical super typhoon territory. The lowest recorded Atlantic hurricane central pressure belongs to Wilma in 2005 at 882 millibars. If Arthur breaks that record while still over the Gulf, it is not a statistic, it is a warning. The third signal is forward speed. Arthur has been crawling at roughly 9 kilometers per hour close to stationary, maximizing every hour it spends drawing heat from the loop current. If you see reports that the storm has accelerated to more than 18 kilometers per hour northward, that tells you Arthur is finally moving off the warmest water and toward shallower, cooler coastal shelves. Acceleration is generally associated with weakening, or at least a plateau in intensification. Still dangerous, but a different kind of dangerous. Conversely, if the forward speed stays below 10 kilometers per hour through tonight, Arthur is still feeding. Every hour of slow movement at this point is another hour of thermal loading. The fourth signal is the evacuation order itself specifically, whether the National Hurricane Center upgrades its advisory language to catastrophic, and whether mandatory evacuation is extended into the interior parishes of Orleans Parish. The coastal zone is already under order. What matters is whether that order expands inward to cover the city core. When that happens, if it happens, it means forecasters are seeing something in the models that they believe justifies disrupting 400,000 additional people. Emergency managers do not issue those orders lightly. The political and logistical cost of a citywide evacuation is enormous. If they pull that trigger, they are looking at something in the data that hasn't made it into the public briefing yet. The fifth signal is the eye wall on satellite imagery. You don't need special equipment to read this GOES 16 and GOES 18 imagery is publicly available and updates every 10 minutes. What you're watching for if the visible eye, which currently appears roughly circular and compact, suddenly appears to grow larger and less defined on infrared satellite. That may indicate the beginning of an eye wall replacement cycle. The outer bands are trying to form a new eye wall. In the short term, the storm may appear to weaken, pressure stabilizes, wind speeds dip slightly. Don't read that as resolution. If the outer eye wall contracts and consolidates, Arthur reemerges on the other side of that cycle with a larger wind field and often with intensified peak winds. An ERC in the 12 hours before landfall is one of the most dangerous sequences a landfalling hurricane can go through. Those are the 5 signals. You don't need to be a meteorologist to track them. You need a browser and 40 minutes of attention over the next 24 hours. Now, what you actually do, if you're on the Gulf Coast, or if you have family there when the evacuation order comes, leave. That's it. That's the whole instruction. Don't negotiate with it. Don't wait to see if the track shifts. Don't calculate whether your specific neighborhood is probably okay. The people who died in Katrina were not foolish people. They were people who made reasonable sounding calculations and ran out of time. A category. 5 storm surge does not give you a second chance to revise your risk assessment. If leaving is not immediately possible, the next priority is supplies for 72 hours minimum, not because help will necessarily take that long, but because in a catastrophic scenario, it might. 3 liters of water per person per day, essential medications, copies of critical documents, insurance, identification, medical records in a waterproof bag, a battery-powered or hand-crank radio that does not depend on the internet or cell towers, because both of those will fail, a charged portable battery pack for phones, cash, because card readers stop working when the power grid goes down. Know your structure. A solidly built 2-story building on high ground is survivable in many scenarios. A single-story structure below sea level in a flood zone is not. For updates, use the National Hurricane Center directly nhc.nnaoaa.gov every 6 hours when advisories are issued. Not social media, not news aggregators that are summarizing summaries. The primary source. The advisory language is precise, and the track cone is drawn with specific probabilistic meaning. Social media will give you terror and misinformation in roughly equal measure at 3 in the morning. The NHC advisory will give you coordinates, intensity, and a forecast discussion written by someone who has been watching this storm for 72 hours straight. And for everyone watching this from somewhere else in the world, somewhere that feels safely distant from the Gulf of Mexico right now, disasters do not send advance notice. What makes the difference always, in every documented case, is not how fast emergency services respond after the fact. It's how prepared individuals and communities are before. A go bag, a family plan, knowing your local evacuation routes, understanding which alerts in your region are serious and which are routine. These are not paranoid behaviors. They are the minimum architecture of surviving in a world where the atmosphere is running hotter, carrying more energy, and producing storms that would have been considered outliers 20 years ago with increasing regularity. The only thing you control in the face of a system like Arthur is what you do before it arrives.